So yeah, I'm Julienne Stroeve, and I am a professor within the Earth Science Department at UCL. I have also been a senior scientist at the National Snow and Ice Data Center in Boulder, Colorado, which is where I did my PhD as well, was at the university there. And I've also been more recently a research chair at the University of Manitoba. I won an award for 7 years to basically do a big research program within Canada as well. Although my interests are mostly Arctic, and for Canada this is good because about 40% of the coastline in Canada is actually in the Arctic. So for them, the Arctic is of course part of their world, so they're very interested in having Arctic science. Now my talk tonight is going to be actually on a subject that I find quite interesting, and that is whether or not the Arctic is influencing your weather. And why I find this topic quite interesting is that, when we try to poll people, we do these sort of, well, in the US, we definitely do these polls to see what people know about science. And, we can ask them questions like, well, where is the Arctic? Or is the Arctic Ocean, or is the North Pole covered by water, or is it covered by land? And, oftentimes people don't know the answers to these simple questions. But if you ask them, is the weather that they're experiencing a result of what's going on in the Arctic? A lot of the respondents say, yes, it is, which I find to be quite curious, because what we understand about linkages in our climate system is a bit more uncertain compared to what we know is actually happening in regions like the Arctic. So yeah, so I'm going to talk about this for the lecture today. And so I'm showing just in my introductory slide an image of the Arctic Ocean at the end of September of 2020, showing you where the sea ice, which is the floating part of the ice in the Arctic Ocean, is at the end of that year in 2020. And then I also show an image of the polar vortex. And this was the polar vortex in January 2020, showing that actually the polar vortex was not so constrained to the Arctic itself. If you look at the wind speed, so the really white areas here, which have very high wind speeds of 360 kilometers per hour, it's actually stretching a bit outside of the Arctic region. Normally we have it focused here over the pole. So anyways, that's going to be kind of my introduction. And yes, when I was a PhD student, I started studying the Arctic, and I didn't study it because I thought that there was anything to be worrying about in terms of climate change. But I did know that, temperatures have been rising, and I like showing this plot because this is the plot that was done by a group in the United States called the Berkeley Earth, and they were funded by the Koch brothers, which was a climate skeptic group, because they really wanted to disprove the fact that scientists have been saying the planet is warming. And so the Berkeley Earth was paid to do a study to try to basically dispute what the climate scientists were saying about how much the Earth was warming. And they actually had to come back and say, well, guess what? The scientists are right. The planet is warming. And so this is just kind of a classic temperature plot since 1850, showing the land temperatures in red and the ocean temperatures in blue. I think what the Berkeley Earth study did was actually did put a bit more larger sort of uncertainty ranges around the temperature records, especially prior to the timing when we had really good station data where we could actually monitor things quite precisely. And then you kind of get here in the 1960s, and definitely since the late 1970s, where those uncertainty bars are pretty much gone, especially with land temperature. And partly that's because later parts of the data record are really based on satellite data, where we can see the entire planet. We can monitor the changes that are going on over the whole planet. We're not just basing it on certain stations. And, we're definitely going through this period right now where the planet is warming quite quickly. And I'm not going to show a plot relative to the longer ice core records, but of course the warming that we're seeing is quite unusual, at least in human lifetimes. So, but in the Arctic, things are a little bit more dramatic. And there was a new report that came out last year by the Arctic. It's AMAP, it's the Arctic, I'm forgetting now the acronym. It's an assessment report done by a bunch of countries, and basically says that we're warming now 3 times faster than the planet as a whole. So when you looked at the previous temperature plot and we see, okay, the planet's warming, actually the warming that's going on in the Arctic is much faster, and it's really centered over the Arctic Ocean region, where we've had a lot of warming, also over Greenland, the Canadian Arctic, but this is where the warming is the strongest at the moment. So Why is that? This is something that is kind of one of the reasons I did my PhD on this topic, was because I did understand that the Arctic is a region that's covered by snow and ice, typically year round. And this is just a snapshot of what the Arctic Ocean looks like in March of 2019. You have a large part of the Arctic Ocean is covered by sea ice. Of course, you got Greenland, you've got all the land surfaces that are also covered by snow and ice. So, you have this frozen region in the north that is quite unique compared to the rest of the planet. Of course, Antarctica is also similar. What happens then? And the thing is that we knew if climate change is going to start manifesting itself, we should probably see signals of this first in places like the Arctic. And this is because snow and ice reflect most of the sun's energy back out to space. And even though, you're in polar dark for half the year, but when the sun comes back up in the summertime, all of that sun is being reflected back out to space. But if you start to melt away the sea ice cover, and you start to melt away the snow on the land, or you start to melt more Greenland, the Earth's ability to reflect the sun's energy goes down. And all of that energy is now being absorbed by the ocean or by the land surfaces. And as a result, you're going to warm up even faster. And it's kind of this positive feedback effect by where you have warmer temperatures, you melt more snow and ice, that warms up the temperatures more, and you just keep melting more snow and ice. So when I started my PhD, I was really interested in how well can I measure the reflective ability of the planet, because obviously if that starts to change, then we should start seeing this runaway warming effect, especially in the Arctic. And so my PhD was entirely focused on trying to measure how much of the sun's energy is coming in to the Greenland ice sheet, how much of it is going out, and the balance between how much is coming in from the atmosphere and clouds in terms of long wave incoming radiation versus how much is going out from the surface. And the energy balance of our planet in general on a larger scale is basically the balance of what's coming in from the sun and what the Earth is emitting out. That is our energy balance. And if that is not zero, then of course, over time, the planet is either going to be warming up or going to be cooling down. And so this is what I did. I worked with satellite data, and I was measuring how much of the sun's energy was reflected back to the satellites, so how much shortwave came out, and also how much long wave came out, which is a reflection of the temperature of what I'm observing. And in particular, I was really interested in measuring the albedo, which is basically the ratio of how much of the sun's energy is being reflected by the surface and how much is coming in. So that was basically the whole part of my thesis project, was really trying to do a good job of doing that with satellites, which isn't easy, of course, because any energy coming in from the sun is going to be interacting with the atmosphere. And this is a very simple schematic. You see it coming down, it reflects out from the surface. But, if there's clouds that have multiple reflections between the surface and the clouds, there's atmospheric gases in the way. So it's not quite this simple. So it was actually a bit of a challenge to do this with some accuracy. But of course, we need to know this delicate balance, because otherwise we can't really, with confidence, say what's happening with the planet's temperature. But it's even a bit more complicated than that. And because if we think about the energy that's coming in from the sun and how much the Earth is giving back, that has to be balanced then by what we call these other fluxes like sensible and latent heat flux. So if something is warming up, it's going to start emitting more temperature back to the air, for example. Or if you have evaporation going on or condensation, you'll get latent heat flux. Some of it could get stored within the surface. So you might be storing energy, for example, in a snowpack, which will then go into melting it. Some of it might get transferred down to the Earth if you had, a shallow snowpack. In the case of the ocean, it might be getting absorbed by the ocean. So it's this whole energy balance of the system that I was really interested in when I started my PhD. And I should say I came from a background of aerospace engineering. So my background was not in climate science originally. I was very strongly educated in terms of how to get airplanes to lift up and how we make spacecraft dynamics work. But what happened to me was I actually fell in love with pictures of the Arctic. And this is why I kind of switched gears and started to focus on climate instead of engineering. But it's still really mathematical. And I think that's one thing I would love to bring out, is that, if you're going to do any kind of climate science, it's going to be rooted in very strong mathematical foundations, which you will see in a moment, because I will show a few equations. Anyway, so this is the energy balance that I was working on for my PhD. And the trick is, you know, if you think when we have newly fallen snow, it reflects about 85% of the sun's energy back out to space. So if you've ever gone skiing or spent time in snow-covered fields and you're not wearing sunscreen, you're going to get not just what's coming in from the sun, but you're going to get 85% of that reflected back from the snowpack, and you're going to get quite sunburned. And I remember the first time I went to Greenland, I was warned that, you know, I should not keep my mouth open too much because you could actually burn the top of your palate because piece of advice said, and I didn't really believe, but so burned like underneath my chin and underneath my nose when I've spent a lot of time in the Arctic. But you know, once we melt off the snow surface, let's say you have ice underneath, so like on the Greenland ice sheet or on the ocean surface with sea ice, then you start lowering the albedo. And what that means is then you can start absorbing more of the sun's energy, and that's going to warm up and it's going to melt more ice. If you completely lose, for example, the sea ice cover, which is covering the Arctic Ocean, then you're going to start absorbing everything into the ocean because the albedo of the ocean is only about 0.03. So that means it absorbs 97% of the sun's energy. So in this way, regions like the Arctic really act as the refrigerator for our planet. So they're keeping the planet cooler than it otherwise might be. And this is why it is so important to study this region. So, you know, what's happening with the Arctic sea ice cover? We have more than 4 decades now of satellite observations that are allowing us to monitor how things are changing on a very large scale. So we can see the Arctic every single day. We can see it whether or not it's cloudy or whether or not there's sunlight or not, because we're working with data that's coming from the microwave portion. And we can really start monitoring the day-to-day changes within the sea ice cover. And, you know, when we've been looking at this, we saw, okay, things are going down. That's okay. We understand that climate's warming. But then we had some really sudden events. We had this big ice loss in 2007, where we lost 26% of the summer sea ice cover within a single year compared to the year before. And that really surprised a lot of scientists because we didn't think you could just melt out that much ice in a single year. And that kind of started things. So since 2007, we've kind of been in this new regime where we just have a lot less sea ice than we used to have in the Arctic Ocean at the end of summer. And temperatures still get cold enough in the winter, we still grow ice, but there's less ice in winter now as well, even though the trends that we see at the moment are really strong in the summertime. And I think what's key to see is that here's Alaska, here's Russia. Most of these regions now are free of ice. Whereas before, the yellow line was what the ice used to be at the end of summer every year. So we're seeing these large changes all along the coastlines of Eurasia and also North America. And, you know, it's a bit, of course, when we have a really great satellite data record, it's quite useful, but it's not that long. And I mean, if you really want to look at climate change in a larger context and, you know, is what's happening today unusual in a longer context, then we have to start using paleoclimate records. And there's a lot of effort right now being done in trying to reconstruct sea ice back in time. This was a study that was done, I believe, in 2011, where they reconstructed sea ice based on other proxies, at least, you know, 1,500 years back. And you can see that today's changes, if you look at the red line, which is what the observations are right now, the changes that we're seeing today are quite unprecedented in at least 1,500 years. Other studies suggest at least 800,000 years. So certainly within, you know, the time that humans have really been adapted to live on this climate and on this planet, we haven't seen such dramatic reductions in the Arctic sea ice cover. So of course, as a consequence, you know, if we are removing the sea ice, we're removing that reflective cover of the oceans are going to start absorbing that heat. And this is just an example of what the mean autumn sea surface temperatures are. Oops, sorry about that. In the Arctic Ocean, of course, if there's ice there, then it's going to be around 0. This is the climatology through 2010, so it doesn't include some of the more recent extremes in the ice cover. But certainly, you know, we have very warm temperatures outside of where the sea ice is. But if we look at the trends over time, we can see that most of the Arctic Ocean, especially the regions where we've been losing a lot of summer sea ice here in Chukchi and the Bering Seas, up all along in the Barents and the Kara Seas on the Eurasian side. You know, we see these changes in sea surface temperatures. So the ocean is warming up, and this is for autumn. So this is at the end of the melt season. So ice is now going to start to reform because temperatures are dropping. But what this does is the ocean cannot freeze again in winter unless it releases all of the heat it gained in the summertime back to the atmosphere. And this is a large part of why the Arctic is right now warming 3 times faster than the rest of the planet. So if I just look, excuse me, this is for 2020. This is just October through December. Should start to form, and there's no more temperatures dropping. But you look at the ocean temperatures, and they're very, very warmer than average, like up to 5 degrees warmer than average, over the regions where we've been losing a lot of the sea ice. And this heat then has to go back to the atmosphere, or you cannot form ice. And so we can look at this spatially over the Arctic Ocean. Here's Greenland and Alaska and Eurasia. We can also look at it by height in the atmosphere. So 1,000 millibars is at the surface. Here we're by latitude, so 30 degrees north all the way up to 90 degrees north. And then we're going up to the troposphere, top of the troposphere in the atmosphere. And you can see there's this warming that is just focused exactly over the polar region. So between 75 and 90 degrees north. This is where all the warming is. It's focused at the surface. So it's really a surface signal of what is going on with the loss of the Arctic sea ice and why you have this big warming that happens in the autumn. So then we have to start thinking about, well, what are the physics here? Because obviously now the Arctic is warming faster than the rest of the planet. And is this going to matter for us? I mean, of course, there's local impacts that we have to worry about. But if we're thinking about why should you care if you're living in the UK, or why should I care if I'm living in the US about what's going up in the Arctic? You might be sad about species changing, loss of like iconic species like the polar bears or seals being in trouble, but will it really impact you? And a lot of it has to do with the fact that we get a lot more solar insolation, of course, at the equator. This is where most of the heat goes. The polar regions receive a lot less of a solar input, so they tend to be colder. And because of that, you have this temperature differential between the equator and the poles. And really the whole point of our weather patterns and our ocean circulation is basically to take the excess heat that we're getting at the equator and move it poleward, because you want to equalize things around the planet. You want to make everything a bit more equal. We got this excess heat, we need to move it. And that is what drives our big, large scale weather patterns. So then you can start thinking, well, okay, if I'm warming up the Arctic faster now, and say I'm keeping this constant, the temperatures here constant at the equator, but this is getting a lot warmer, how would that start to affect our weather patterns? Because maybe our weather doesn't need to move so vigorously anymore to move the excess heat that's being gained at the equator to the poles, because now the poles are getting a lot warmer. And there's a lot of research going into this right now, because obviously if I think about human society, what are we going to care about? We're going to care about extremes in weather. We're going to care about, you know, how much precipitation is going to fall, where we can grow our food. Of course, sea level rise is something that I'll just touch on briefly, but these are the things when I think about society and as we go forward under climate change, which is really going to matter. So there's a couple things that happen, and that is because one, we have very different temperature distributions on the planet. So we had the solar insolation on the previous plot. This is just a graphic of what the air temperature is at a height of 500 millibars in the atmosphere. So we're not at the surface, we're kind of midway up in the troposphere. And we can see, okay, here's the equator region. This is where we have a lot of the heat. And then this is the polar regions where we don't have very much heat. We can also look at this in terms of the height of the atmosphere, because the amount of heat that we have near the surface actually determines how high the atmosphere goes in terms of the geopotential height. So if you have a lot of warm air below, you're pushing up your pressure levels so that you have more height at the polar regions, and you have lower heights and lower pressure in the polar regions compared to the equator. And this sets up this north-south or equator to north or equator to south temperature gradient that basically also means that air is going to start flowing from regions where you have warmer temperatures or high pressure to regions where you have lower temperatures or lower pressure. And that's really the physics that we care about when we're thinking about how could what's going on in the Arctic now start to impact your weather at lower latitudes. And, you know, it's hard for me sometimes because I did come from engineering not to want to show equations. But I also think, you know, when you're learning your maths and you're learning about these equations and calculus, it all has applied applications, especially in climate science, because we rely on these relationships massively to understand the physics of climate and how things are changing. So what I was trying to explain is that, you know, we have this warm air at the equator that is giving a thicker atmosphere overall. And this is what we can see here at the equator. And then we have the colder temperatures at the poles, and we have, you know, a little bit thinner atmosphere at the poles. Basically, for the same pressure level, if I am going to be at 5,500 meters, it's going to be much lower with lower pressure here than it will be at the equator, which will be much higher. And so we can measure the thickness of the atmosphere between two different pressure levels. Sorry, that should be a Z1 here. But based on just the temperature of the layer between the two altitudes, so if I'm at 0 versus 5,800 meters, that will give me a temperature, an average temperature for that layer, and I can relate that to the pressure differences. And it's really just a simple relationship that we use because it really just shows us that the thickness of our atmosphere can be greater, the temperature is greater, and because of that, we can look at flow in the atmosphere. So if I just think about our planet as a whole, and I think about, we have this cold layer of atmosphere that stretches from the tropics all the way to the polar region where it's much colder. And, you know, we know that air is going to start expanding because it's warmer, because we have that relationship between pressure and temperature and the height in the atmospheres. And air is just going to want to flow down that hill and go to the Arctic. But as we, and of course, yeah, I'm sorry, the Earth is also spinning, of course, underneath that. We get this Coriolis effect, and that creates our large-scale jet stream, which drives our big weather patterns. But if I start to warm up the Arctic faster, I'm going to start flattening that hill. So does that now weaken the jet stream? And that is the big question that we have at the moment in climate science. Are we weakening the jet stream? And one way that we could describe this is, you know, if you just think about an air parcel, it's not going to move unless there's some sort of forces acting on it, right? So you have to have forces that will create movement in the atmosphere. Now, you can have an air parcel in one location compared to another location. One might have higher pressure, one might have lower pressure. And it's natural then for the air to want to flow from high pressure to low pressure. So we have this pressure gradient force that will act. So if we have high pressure at the tropics and we have low pressure in the poles, the air is going to want to move that direction. But you have the fact that the Earth is spinning underneath it. So we get this other force, which we call an apparent force, caused by the Coriolis effect, that will depend on where on the planet you have your air parcel. So if I'm at the equator versus 30 degrees latitude or 90 degrees latitude, I'll have a different amount of force acting on it based on the Earth's rotation. And then, you know, what else can influence my air parcel? Well, if it's close to the surface, I might have a lot of friction from topography, for example, that might slow the flow down. And I also have gravity that can also be acting on my air parcel. And that mostly influences things in the horizontal direction. But Newton's second law basically describes all the forces that you would experience on an air parcel as a function of differences in pressure, the function of the Earth spinning below us, gravity, and friction. And this is also true for the ocean. So this same equation is used for ocean motion as well. And it basically just says the change in motion, so velocity, dv dt, is going to be a function of the Coriolis effect, which is this term here, your pressure gradient force, which also depends on the density of the air, your gravity, and your friction. It's a very simple equation, but this equation is what's used for all of our modeling of what is driving motion in the Earth's atmosphere. So if I'm thinking I'm way, way high up in the atmosphere, so I'm pretty far away from friction, so I'm not worried about topography or mountains interrupting my flow, and I'm just going to neglect vertical motion and just care about winds that are blowing from east to west or west to east, and are worried about the winds blowing from north to south, for example. Then we have what we call the geostrophic wind equations. And this is what meteorologists use to look at flow in the atmosphere. And this is what basically dictates our large scale weather patterns. So we're caring about the zonal flow, which is what's coming from west to east. And we care about the meridional flow, which is what's going from, say, the equator to the poles. And this is just a balance between differences in pressure and the fact that the Earth is spinning below us. That's very, very simple. And so we can get the components of the wind speed in the zonal from east to west, or to east. Here by U, this F is your friction, this is your density, your change of pressure with latitude. Or you can look at your meridional flow, which is from the equator, for example, to the pole. Again, it's a function of the Earth's rotation, the density of the air, and the change in the pressure versus longitude. So you can look at it in terms of pressure. We can look at it also because pressure and thickness are related. We can look at it in terms of how thick the atmosphere is. These are very simple equations, and they pretty much explain everything that goes on in terms of just large scale weather at the position of where the jet stream is located, which is quite high up in the atmosphere. This would not be valid if we were at the surface, because we would have to deal with friction and topography. So I know this is a bit mathematical, and I wanted to show this because I really feel like it's really important to understand that all of this kind of physics is grounded in math. And if you're doing climate, you're going to have to do quite a bit of math in your studies. So this is kind of why I show this. I do find it sometimes can make people feel a bit nervous, but I like the idea that you can apply this in a real world case. So I don't know if you've heard about within your lectures about the ideal gas law, which is basically just a relationship between pressure and temperature and the density of an air mass or volume of an air mass. So that if you have a constant volume of, say, a cylinder filled with air, you increase the pressure, you're going to increase the temperature. It's kind of how a pressure cooker works. So this is a law that we use all the time. It's very simplified, but by doing that, we can just write things in a way that we can just change if we want to write how the wind speed will change as a function of temperature or how it will change as a function of pressure. We can just rewrite it by using these substitutions. So I can say the density of an air parcel, for example, is equal to the pressure of the air parcel divided by the temperature. And this is just a constant by the ideal gas constant. Or I could also say the pressure is just equal to the density of an air parcel proportional to its temperature. Very simple relationships. And they just allow us to reformulate our equations of air motion in the atmosphere as a function of what is the data we have. If I know the temperature difference, for example, here as a function of latitude, so say the latitude temperature difference is changing because the Arctic is warming faster, this is all constant, so I don't care about this, then how will that change my wind speed? This is what I care about, because the wind speed changes are what's going to influence your weather. So we can just start taking some examples, and I could just say, okay, well, what does my temperature look like in the atmosphere at different levels in the atmosphere as a function of latitude? And that's just what I'm showing here. I just took some data that's available from satellites and models. This is my temperature, for example, at the surface. So 1,000 millibars, which is actually at the surface of the Earth. This is the South Pole. This is the North Pole. So it's obviously winter because the North Pole is colder right now. And this is here at the equator. So we have this temperature dropping off quite rapidly as we go further north. That's at the surface. If we go up about 500 millibars in the atmosphere, you still get a drop off. It's not as rapid, but you still have a drop off. Or it could be here really at the top of the troposphere, getting closer to the stratosphere. There's still a change of temperature with latitude, although it's much, much less. But I can start looking at these relationships and I can say, okay, well, what if I start increasing these temperatures here? And I change this slope of this curve. So I'm no longer having such a big change with latitude, for example, in my temperature. What will that do to my winds? So if I just take an example and I say, okay, well, I want to know what the wind speed will be at 250 millibars, which is about the height of a jet stream. And I know that my wind at my surface is about 5 meters per second. So, not super strong, but there's some wind blowing. And then I assume, for example, that the temperature for my whole atmospheric layer between the surface and the top of the jet stream is a certain value. And then it's dropping off at a rate of 0.75 degrees Celsius per 1,100 kilometers. So I'm losing not quite a degree per 1,100 kilometers that I go further north. What will that do to my temperature? To my wind speeds? So I can easily just put this in. I can say, okay, well, if I have my wind speed, the wind speed at the surface as a function of how the temperature is changing with latitude, which is this value here, the 0.75 degrees per 1,100 kilometers, and then just the pressure differences in the atmosphere. What would that give me? And I could say, okay, well, I know my surface wind speed is 5, and this is my Coriolis effect, this is my pressure differences, and this is my change in temperature as a function of latitude. And I get a strength of a jet stream that's about 41.8 meters per second. But now if this is getting smaller and I don't have such a big change anymore in my temperature with latitude, then the jet stream speed is going to start to slow down. So I can start reducing this value. So that is what we're concerned about right now. If I think about what's going on in the Arctic and will it affect my letter down here, is how am I changing this temperature gradient with latitude? This is just a nice plot that shows you that wind speed. So the U component of the wind speed, which is our zonal wind speed. And you see right here, this is 200 millibars in the atmosphere. This is our surface down here. This is where you have these really high wind speeds. So we're looking here at like 45 meters per second is my wind speed. These are my 2 jet positions. And this is a winter time. So this is when the Arctic is colder, the jet is much stronger right now in the Northern Hemisphere during this time of year. And this is what's going to move all of our weather and determine what's going on where you are. So the question is, well, what's happening with the speed of a jet? And this is a lot of research that's been going on in the last few years. And it's quite controversial because there's a lot of things that affect our weather systems. I'm kind of simplifying things right now in terms of a temperature gradient between the equator and the poles, but there is some things going on here that we maybe have to pay attention to. So I'm looking at October, November, December average. I'm looking at a wind speed here that was at 500, so it's a bit lower. It's actually right here. And this is from a plot from a colleague of mine. But this is my zonal wind speed, the solid line over time. So from 1979, this was through 2012, my zonal wind speed. And this is my sea ice that's been going down during that same time period. So the studies have been suggesting, well, okay, here's my wind speed, which is my speed of my jet. It's going down. The sea ice is going down. Are these two then related? This is a big question. And just because you have 2 things happening at the same time doesn't necessarily mean they are related, even though physically we can say, yeah, I understand if that temperature gradient is changing. And of course, by the thermal wind relationship, we should start to slow down these wind speeds. And we do see the wind slowing down. That's not disputed. The wind speeds are slowing down. So, but it's not just the wind speed that matters. And here's a nice animation that NASA has put out showing the jet stream. And what's interesting about the jet stream is, sometimes you see it moving with very small waves and it's moving quite fast. So when you have small waves, the jet moves very fast. But when you start seeing it get wavier, the jet stream starts to move a bit slower. And so then there's some argument, well, okay, if I'm going from a regime where the flow was quite zonal, where you had a very strong U component of the wind speed, but a very small V component, which is the meridional wind speed, then weather systems move quite fast. So whatever weather you have here is moving very fast across, say, North America over to Europe. But if it's wavy, it's going to move a bit slower. And that's the question, is are we not just impacting the wind speeds, but are we also impacting the waviness of the jet stream? Because if the jet is moving slower, if it is wavier, then whatever weather is underneath that jet stream, so if you have a high pressure or low pressure, it's going to get stuck there. It's going to stay there longer. So whatever weather you have, whether it's rain or whether it's heat, it's going to move slower. It's going to be stuck in that position for a longer amount of time. So yeah, I mean, the question is, well, do we have these extreme weather events increasing, and are they related to climate change, and are they related to what's going on in the Arctic? I mean, that is the million-dollar question. And of course, this is getting a lot of attention because we do see that extreme weather events are increasing in frequency over time. And this is just an example for the US from 1980 until 2020. And it just shows the number of events by type. So whether you have very severe storms, these periods of tropical cyclones or wildfires, you know, frequency of these events is increasing over time. And of course, the cost of these events is massive. You know, you're looking at 120 billion per year in damage from extreme weather events. So of course, as society, we have to care massively about this, because it's not just that, you know, maybe you have to deal with extreme weather, but you're also having to deal with huge financial losses now. And as we try to think about climate change in the future, we have to adapt to this. And, you know, I mean, it's hard to not open up the newspaper and just see these extreme weather events anymore. We had a really extreme case in Massachusetts where we had huge storms that were created in part by, you know, sea level rise, which is definitely going to give you more coastal flooding, but also extreme temperatures, big massive flooding, for example, in the UK in 2014, big flooding in Alaska in September 2012. In Greenland in 2012, we also had massive flooding. This bridge that had been there for almost 100 years was washed out because you had incredible melt of the Greenland ice sheet that summer. Deep freezes in Europe are becoming more common, even snow in the Black Sea. I don't know where this picture came from, but a colleague uses it, which I think is pretty cool. Giraffes in snow. Big snowstorms in Japan in 2012. And, you know, here's a nice beach scene, which doesn't seem that unusual, but that was in March in 2012 in Burlington, Vermont. So we're having this strange weather happening. We have huge droughts. We've got heat waves that have killed like 50,000 people in Russia, for example. We have ongoing droughts. I should update this because it's not just those years. We have these massive droughts that are extending. So the question is, well, what do all of these events have in common? And really what it is that the weather patterns are stuck. That is the key thing that's driving an increase in extreme weather for the planet as a whole. So then it just really comes down to, you know, are what's going on in the Arctic impacting the jet stream to the point where we know it's moving slower, but is it also becoming wavier so that you have these bigger fluctuations in the jet that actually keep things stuck in one position for a much longer time? And this is actually quite controversial still, because while everything on the planet is interconnected, and while we know the Arctic is warming much faster, and we know that theoretically it should start changing the speed of the jet, whether or not it's getting wavier, and whether or not you're getting these cold air intrusions coming down from the Arctic, for example, where you get really cold air that maybe hits warm, moist air masses coming up from the equator, and you get massive snowstorms or really frigid temperatures. You know, that's something that's a bit less clear at the moment, but there's a lot of research that is for sure going into this topic. But really, any extreme weather event that you have, whether it was a flooding in Germany last year or, you know, the beast from the east, all of it has to do with a big blocking pattern in the atmosphere. So you're going to have a big kink in your jet stream. That is what causes an extreme event. And so extreme waviness is the key thing. And that's what we're really having to focus on within climate science these days, is how does this pattern change with time? There's another thing that you've probably heard about, and that's also the polar vortex. And typically you have this cold air that is constrained within the Arctic, also over the Antarctic, and that results in a very stable polar vortex. And that polar vortex is very strong. It keeps all the winds circulating very fast and the stratosphere above the Arctic Ocean, for example, and all the cold air is kept there. If that polar vortex is disrupted, then you get these lobes of the polar vortex that move south, and then you get this cold air that comes south. And that's where you get these really extreme temperatures, for example, in the middle of winter. So even though climate change may say, okay, the planet's going to warm and temperatures should get less extreme overall, you can get these disruptions in the polar vortex, which actually causes a lot of cold air to come down, and it comes down quite quickly. So what's driving that disruption is something that I think scientists are becoming a bit clearer about. And part of that has to do with the fact that when you have less ice in the Arctic Ocean and you have more heat, so you have an ocean now that disrupt the vortex and actually cause the weakening of it so that you actually start having colder air spilling out of the Arctic, for example. And we had it just last week in North America. We had really frigid temperatures again. In 2021, they had it also where they had snow all over Texas and they had huge power outages, and there was 20 billion in damages as people lost a lot of power. You had 150 deaths. This seems to be directly linked to what's going on in the Arctic. So because we just have less ice overall and the ocean surface is actually much warmer than what it would be if it was ice covered, it can perturb the polar vortex so that these kinds of extreme events are becoming more frequent. And it's not that you can say one individual storm is maybe a result of what goes on in the Arctic. It's the changes in frequency of these events. So, and we're seeing that they're becoming more frequent. We're seeing this weakening of the polar vortex. We're seeing a weakening of the jet. And this means that these kind of events are going to become more common, even in the face of climate change when the planet is warming overall. So then the question is, what will the future hold? And, you know, I do think in all of your guys' lifetimes, you're going to see an Arctic Ocean that loses its ice in the summer times. We've done a lot of studies where we've been able to quantify how quickly the Arctic Ocean is going to lose its sea ice based on how much more CO2 we put in the atmosphere. At the moment, that gives us a threshold of global warming of 1.7 degrees Celsius before we start seeing summers that have no ice. But it's not just that we lose the ice in summer. I mean, if you go to 2 degrees, you're going to be ice free for maybe 3 months of the year. If you go to like 3.5 degrees, you're going to be ice free for maybe 5 months out of the year. And so, you know, at the moment, we're looking at a minimum overshoot and our target for temperatures of 2.7 degrees Celsius. This means at least 3 or 4 months with no ice in the Arctic Ocean. This is a huge climate shift, and this isn't something that's happened in our lifetimes, and certainly not in the lifetimes of human evolution on the planet. And, you know, we're currently on target for about 4.5 degrees Celsius. So we're looking at ice-free conditions for a much longer time. This is going to warm up the Arctic massively. And this is why when you see governments negotiating 1.5 degrees limits or 2 degree limits for the Arctic, for the globe as a whole, the warming in the Arctic is actually a lot larger. And so if I look at the 2 degree climate scenario at the moment, so if we have a global warming of 2 degrees, the warming in the Arctic is up in here, especially in October, November, December. This is because you've lost the summer sea ice and the ocean has gained all of that heat, and you're looking at a warming of around 8 degrees Celsius in the Arctic at the moment. This is a reality that we're facing. In the summertime, the temperatures are not going to warm that much more because all the energy is going into melting the ice. But it is in the wintertime and also in the springtime where you're having much larger warming in the Arctic compared to the rest of the planet. So we think, 1.5 or 2 degrees is unacceptable where we live, but can you imagine 8 degrees of warming, in your region, which is what the Arctic is looking at the moment. So then the question is, of course, well, how is that going to impact weather extremes in the future? And we know our planet is going to continue to warm. The Arctic is going to continue to warm much faster than the mid-latitudes. Is that going to really keep changing these frequencies and intensity of extreme weather events? For sure, one thing you will do is you're going to have more open water. You're going to have more fuel for storms. We already see that precipitation in the Arctic is going to increase under climate change. So because the atmosphere can hold more water vapor if it's warmer, but also now you have water instead of ice. So you have a moisture source. And eventually that's going to transition from snow to rain. That is something we already see in the Arctic by the end of the century. How it's going to impact the intensity and frequency of extreme weather events in the lower latitudes, I think, is still a bit uncertain because we have to run models for this. They're not perfect, but at least the latest IPCC report does show that, you know, for sure these changes that we'll be seeing in the future would not be happening without climate change on top of it. And of course, you know, if I think about the Arctic warming up to 8 degrees, well, you know, there's about 7 meters of sea level rise within Greenland itself. So you're obviously going to start contributing to sea level rise by losing the Arctic sea ice, for example, even though, you know, the sea ice in the ocean is like an ice cube in a glass of water. If you melt it, you're not going to raise sea level, but you're actually warming the Arctic even further. So that impacts on Greenland and its contribution to sea level rise. The Antarctic has been slower to respond to climate change, in part because it is a different area. You've got land on the South Pole surrounded by ocean. It's also starting instabilities, especially when we look at the West Antarctic ice sheet, which is really contributing a lot more now to sea level rise than it used to. So then if you think you've got sea level rise on top of this, and you've got extreme weather, the storm surges from a storm will be so much larger, and the flooding will be so much larger than we had anticipated. And then there's the fact that, you know, large parts of the Arctic landmass are all frozen soil, and these have been frozen soil year round, and they're starting to thaw. And there's currently estimated about 1,400 gigatons of carbon locked in the frozen ground in the Arctic, or actually in the Northern Hemisphere as a whole, compared to 850 gigatons in our atmosphere at the moment. So as the permafrost thaws and this carbon gets re-emitted to the atmosphere, either as methane or as CO2, it's going to enhance the warming even faster. And this is something that our models aren't doing a good job with at the moment. And so the warming could be much worse than we're even projecting at the moment, given current negotiations with emissions of greenhouse gases. And, you know, even though the polar regions feel quite remote, they do shape our daily lives. I mean, if you think about sea level rise, you think about biological activities, ocean circulation patterns, atmospheric circulation patterns, everything is controlled by this delicate balance that we have on our planet, which depends on large parts of the poles staying cold and covered by snow and ice year round. And we're starting to change that delicate balance. And this will impact all of our daily lives, not just those that are living in the Arctic directly. And I think for me, the reality is, and what's becoming more sobering in my lifetime is that, you know, governments around the world are not prepared for an Arctic Ocean free of sea ice. I mean, this is something that we don't know the full outcomes of. We're doing this huge experiment at the moment. We try to run models and we try to simulate what we think will happen, but we really have no idea. And of course, the people living in the Arctic are being faced with this every day. You know, the whole ways that they trust the weather patterns, the whole ways that they go out and hunt on the ice, the stability of the ice is changing. You have so many more accidents, people falling through the ice. Where the species are migrating to is changing as a function of the ice conditions changing. That threatens our food and water security, that threatens flooding, that threatens a whole hydrological cycle, all of our infrastructure. Everything is being threatened by what's going on in the Arctic today. And we're really just not prepared for this. And so I think, you know, I'm getting a bit more skeptical. Like I feel like these changes are about to happen on a large scale in the next 20 years. And we need to start adapting to this future reality. And so I will just leave it there. This is just a photo from an expedition that the Germans did for 2019 through 2020. It was a year-long expedition where they froze their ship in the Arctic sea ice. And I was a lucky person to get to go on this expedition. And really what we did is we had this multinational effort for scientists around the world to come together, collect as much data that we could to help improve our understanding of processes going on in the Arctic so that we can better do a job predicting what's going to come into the future. Okay, and I guess that will be it.
Brilliant. Thank you so much. So the Q&A is open, so if you have any questions at all, do pop them in there and we can read out your questions here on screen for you. But to kick the questions off, I do have a question for you actually. It's a little bit different in that it's more about you and your career. So I imagine people thinking about their A-levels, and you showcased exactly how physics and maths A-levels get used in climate science and just how linked they are. But what would a career in climate science be like? So maybe not a typical day, but a typical year. You know, what could you expect if you became a climate scientist yourself? What would it be like, do you think? How would you describe it?
Yeah, well, my favorite part of climate science would be when I get to actually go into the field and observe what it is that I'm actually studying. I mean, most of my work, I work with satellite data, so I process data coming from satellites, and I try to retrieve, you know, different variables from the satellites, because, you know, satellites are just sensing energy and you have to convert that into something meaningful. So if you want to know the temperature, for example, you need to do conversions for that. If I want to measure the albedo or how much sea ice is there or how thick the ice is, I have to do conversions. And so when I go into the field, I like to do these physical experiments to try to better understand how I convert this energy that I'm receiving from the satellite into something meaningful. So a lot of my work is on that. And then, of course, I'm really interested in understanding we care. It's a harder question. So that then means you work with other scientists and other disciplines, which I think is quite exciting too. So if I want to understand, well, how does the changes in the ice influence, you know, fish in the Arctic Ocean, I need to work with marine biologists, for example. And I find that part of my work quite rewarding, is to work with other people in different disciplines.
It sounds so exciting, you know, seeing just some of the pictures and even just hearing different places that you've been in field work. It sounds like your job is kind of partly very mathematical, theoretical, but also kind of getting out there and seeing these places that most people might not be able to see or get a chance to sort of visit. So that sounds pretty amazing. So my other question for you was a little bit more about sea ice and land ice. So I've been learning a bit myself about the Arctic and a bit more about it. So can you tell us kind of the difference between land ice and sea ice? Is it just that? Is it sea ice is just in the water, land ice is on land? Or maybe some of the impacts that those two melting might cause?
Yeah, well, sea ice, of course, is ice that forms in the ocean itself, whereas land ice is forming on land. And so as a result, I mean, when you melt sea ice, it's not going to necessarily raise sea level because it's like an ice cube in a glass of water. So it's already floating on the ocean surface. It's not going to displace anymore, or it's not going to lead to any more sea level increase if you melt it. But it does influence the temperatures dramatically, for example. So it kind of indirectly also influences sea level rise through warming up places like the ice sheets, the glaciers around there that can then dump more fresh water in the form of icebergs or just freshwater melt from the glaciers as well into the ocean. So, you know, if I think about, it's not just, so you have land ice, of course, that does contribute to sea level rise, but you also have in Antarctica, for example, big floating ice shelves that are also already floating on the ocean surface. So those also are not contributing now to sea level rise because they're already floating on the ocean. But those breaking up holds back all this ice behind it. So it's like a dam breaking. And this is also why we care a lot about that. And sometimes sea ice influences that stability as well, because you can have ocean ice and you can have the floating ice shelves from the land, and they kind of are all locked together. But if those start to break up, it's like the dam breaking and all the ice behind it can start flowing into the ocean.
Right. So my final question for you before we sort of wrap up this evening would be one piece of advice for maybe an aspiring scientist. So someone studying their physics and maths A-levels, aspiring to be a climate scientist, what could be maybe one piece of advice you might give them?
Oh, that's a good question. Yeah, you know, I think sometimes it's hard because I don't know how often we do applied science. I mean, I came from engineering, so everything was quite applied in what we did. So all the math that you learn and all the calculus, I mean, you're always doing an applied thing with it. And I guess what's so nice about climate science is a lot of these stuff that you are learning in your A-levels and your physics classes, you then get to apply to real world problems, and you actually get to see it happening as you go. So if I was focused here on weather, But obviously, you can measure these things. You can put weather stations up and you can see how these fluxes are happening. And so I think, when you're in school and you're just doing things in books and you don't actually get to do the applied work, but if you get a chance to actually go in the field and you make your measurements and you start to apply these concepts that you're learning within your books and to real world data, it's a lot more exciting that way. And I really encourage that, because oh my gosh, when I did my aerospace engineering degree, I was learning about, how to make rockets work and things like that, but I never actually got to see a rocket. I just had to solve the math of the fluid flow going through the combustion engines and everything. And you're like, well, okay, I can do the math, but do I care? Because I don't actually get to see this. And so I think what's exciting about climate science, and especially, when you start doing these fields that are very societal relevance, and you get to go there and you get to work with people or work with the natural environment, it's quite exciting.